Hi everyone, hello and welcome. So today we're talking about piecewise functions. We've actually already considered an example of a piecewise-defined function. That was the absolute value function. So we'll start with this example. So first, just in terms of our definition, well, we say a function that's represented by different expressions on different parts of its domain is called piecewise-defined. Here's our example. Our first example, f of x is equal to the absolute value of x. That was piecewise-defined. Right, so for positive values of x, this function is just the line y equals x. But for negative values of x, it's defined as the line y equals minus x. Right? So what does this graph look like? Well, there's two different segments. There's one with a slope of 1. This is the line y equals x, and one with a slope of negative 1. This is the line y equals negative x. Remember why that's necessary. For negative x, we need to take its opposite. So if x is negative 2, we need to define the absolute value as negative of negative 2, positive 2, which brings us to here. If x is equal to negative 4, we have to define the absolute value as negative of negative 4, positive 4, puts us here. However, if x is positive 4, we just define it as 4, positive 4. So we're on the line y equals minus x for the negative values of x, and line y equals x for positive values of x. Hence we say the absolute value of x is piecewise defined. Okay, we have other examples, so there's other things that can happen. So for instance, consider the graph of the function y equals g of x, given these expressions. Suppose g of x is just 2/3 x plus 1 when x is less than or equal to 3, and g of x is equal to 5 for x greater than 3. So we can use bracket notation to make this concise. We just say, here's the upsloping linear portion, the 2/3 x plus 1, for x up to 3, for x 3 and less, and then for x beyond 3, we're at 5. So you can think about what this is going to look like. We're going to have this upsloping portion, and then we're going to have a flat portion. And more precisely, we're going to have an upsloping portion, closed circle, upward jump, and then flat at 5. Let's go back and make sure that makes sense. So this is saying we're going to have a closed interval up to 3, and we're going to have an open interval beyond 3. Is that correct? Sure. So 2/3 x plus 1, closed interval up to 3. It's inclusive of 3. And then for values of the domain past 3, we have an open interval. Yep, so indeed that's correct. Solid dot shows that it's included for the graph x is less than or equal to 3. The open dot shows it's not included in the graph for x beyond 3. Here's another example. So suppose we have a data plan for a smartphone. It charges 99 cents per day for data usage up to 20 megabytes, 7 cents for each additional megabyte or part of a megabyte. We can use bracket notation to write a formula for the daily cost C of the data plan as a function of the number of megabytes m. We can graph the function and state the domain and range of the function. Okay, so I'll stop it, let you get a chance to do this on your own. And then we'll resume. So here is how we can organize this data into bracket form. Data plan for the smartphone charges 99 cents per day up to 20 megabytes. Okay, so this tells us we're going to be at a flat rate of 99 cents per day as long as our usage of megabytes is less than or equal to 20. Right, we're going to start with 0, we're going to go all the way up to 20, and then beyond 20, they have a different pricing scheme. Now it's going to be 7 cents for each additional megabyte or part of a megabyte. So I have 7 cents times megabytes used beyond 20. And then why plus 99? Oh, it's because we're going to start with 99 cents and then we're paying another 7 cents for each additional beyond 20. And that is exactly what this portion is getting us. This term, this quantity m minus 20. Think about how this is working. Suppose m is 20. This drops out. This is just 0. Suppose m is 19. Well, then this is going to be negative 7. Or well, 19 minus 20 is negative 1 times 7, negative 7. So we'd be at 92. That's not the price. They're not going to let you get by with 92 cents for your usage of 19 megabytes. No, they're charging you 99 cents all the way up. what about for 21 megabytes? Oh, for 21, now we're going to have 21 minus 20. That's 1 beyond, and we're going to get an additional 7 cents. So then we're going to be bumped up to what? 106. Yeah. Okay, so this indeed is working correctly, but it's not nice to look at. So let's collapse this. It's very nice to interpret. When we look at it this way, we can see, oh, megabytes beyond 20 incur another additional 7 cents. Well, we can simplify this to 7m minus 41, which doesn't have nearly the same ease of interpretation, but is much more concise to deal with. Okay, and it's mathematically equivalent. And here's the picture. So we're going to be a flat level of 99 cents all the way up to 20, and then beyond 20 megabytes, we're going to be this sort of upward sloping line, 7m minus 41. What does this minus 41 tell us? That's the intercept of this line. So you can see maybe I haven't drawn this perfectly accurately. We would want this to go through negative 41. Yeah, you can see my slope is not a slope of 7, is it? All right, well, let's just pretend this actually goes through minus 41. Sorry about that. Not going to fix it, though. All right, from the graph, we can tell the range is going to be C is bigger than or equal to 99. Why? Well, the minimum value for C is going to be 99. You're not getting out of this plan for less than 99 cents a day. And then it can go positively, probably to infinity, although at some point people are just going to cancel their plan. We know negative data usage doesn't make sense. The domain has to be m greater than or equal to 0, right? You could use 0 megabytes or any positive amount, though of course there's going to be some physical limitations, but mathematically we'll allow any m greater than or equal to 0. Cool, so our domain, m greater than or equal to 0, our range, c greater or equal to 99, and we see this from the graph. So one last example. The Ironman Triathlon is a race consisting of 3 parts, 2.4-mile swim, followed by a 112-mile bike race, 26.2-mile marathon. Participants swim steadily at 2 miles per hour, cycle steadily at 20 miles per hour, run steadily at 9 miles per hour. Assuming no time is lost during the transition from one stage to the next, find a formula for the distance covered, d in miles, as a function of the elapsed time, t in hours from the beginning of the race, and graph it. Okay, so what are we trying to do? We are trying to find a function that'll give us the total distance covered, d, for a given elapsed time, t. So we want to know the total distance at 2 hours into the race, for instance, at 3 hours into the race, at 5 hours into the race. If we have done our function correctly, it will be able to answer those questions. It'll be able to tell us what is the total distance covered after 4 hours. That's what the function has to be able to do. All right, so make that happen. Go ahead and work this out. It's a little bit involved. All right, so hopefully you've stopped and started the video. For each leg of the race, we'll use the formula distance equals rate times time. First, we'll calculate how long it took for the participant to cover each of the 3 parts of the race. Well, the first leg swimming 2.4 miles at a rate of 2 miles per hour tells us this took 1.2 hours. Second leg was 112 miles divided by 20 miles per hour biking, so 5.6 hours. And then the final leg, 26.2 miles running divided by 9 miles per hour, is 2.991 hours. Okay, so the total finishing cumulative time is the sum of the hours spent on the first leg, the hours spent on the second leg, and the hours spent on the third leg, 9.71 hours. And a marathon in under 3 hours is pretty good, especially after having done all the swimming and biking, though a 3-hour marathon is in itself is not elite. Okay, during the first leg, time is less than 1.2, right? Less than 1.2 hours has elapsed during the first leg, and the speed is 2 miles per hour. This says the distance for the first leg is equal to 2 times t, right? 2 times t, 2 miles per hour times the time during this interval from 0 to 1.2 hours. Okay. During the second leg, this is between 1.2 hours and 1.2 plus 5.6 hours. Why 1.2 plus 5.6? Oh, we spent 5.6 hours on the second leg. So the second leg is going to be the time between 1.2 hours and 1.2 plus 5.6 hours. So this is going to be an upper bound of 6.8 hours. So when the clock, between the time that 1.2 hours has elapsed on the clock and 6.8 hours has elapsed, the participant is on the second leg. Before 1.2, they are on the first leg. After 6.8, they are on the third leg. When the participant is in the second leg, the total distance covered is the sum of the distance covered in the first leg, 2.4 miles, plus the part of the second leg that has been covered by time t. So 2.4, the distance covered in the second stage, 2.4, or total distance covered during the second stage, 2.4 plus 20 times t minus 1.2. Right, 20 miles per hour times some time minus 1.2. So the distance covered is 20t minus 21.6 for the range for times between 1.2 hours and 6.8 hours. Okay. Where did this 21.6 come from? We're just distributing, right? Okay. In the third leg, this is between 6.8 hours and 9.71 hours, which is the final clock time. The speed is 9 miles per hour. Since 6.8 hours were spent in the first two parts of the race, the length of the time on the third leg is t minus 6.8 hours. Thus, by time t, the distance covered on the third leg is 9 times t minus 6.8 for, so I want t, this is what we want. For not just for 9.71, we want this for 6.8 is less than t is less than 9.71. Must have a LaTeX error there. This should be this region right here. And then when the participant is in the third leg, the total distance covered is the sum of the distances covered in the first leg, 2.4 miles, the second leg, 112 miles, plus the part of the third leg that's been covered by part t. So total distance is going to be 2.4 from the first leg, 112 from the second leg, and then 9 miles per hour times however many hours, t minus 6.8. So this is going to be 9t plus 53.2 for this interval of time, for times between 6.8 and 9.71 hours elapsed on the clock. Okay. So here's a way to represent all this in bracket form. So remember, we're trying to get distance as a function of elapsed time. So when between 0 and 1.2 hours has elapsed, the distance traveled is 2 times t. For between 1.2 and 6.8 hours elapsed, the total distance traveled is 20t minus 21.6. And then for between 6.8 hours and the end of the race or the participant's conclusion of the race, 9.71 hours, we have the distance traveled represented by 9t plus 53.2. And of course, this is all resting on the very strong assumption that our participant has traversed this Ironman using a constant speed for each of the three: constant swimming speed, a constant cycling speed, and a constant running speed. That would be very unlikely. Okay, so here is the graph of these components. So here's the swimming portion, here's the cycling portion, and here's the running portion. And this is giving us the distance as a function of the time elapsed. Right? So here we have a very low slope. Here we have a steeper slope, right, 20t, and then a flatter slope, 9t. And this will give us the distance as a function of time, right? So as time elapsed, the total distance traveled is given by the height of the graph. Okay, very good. So let me know if you have questions.